We're going to call this, I guess, models of the atom. We're just going to look at some of the stuff we've already talked about and some of the grade 9 stuff, and we'll just review it so we have something sort of on paper. Because it's kind of a long story. So you have the actual worksheet, or I guess handout that I gave you, which is the long version of the story. We're just looking at the very simple version of the story, where the concept of the atom began as an atom. Okay, so it begins with the concept of atom from the Greek word atomos, which is basically the idea that everything is made of tiny little things. It doesn't tell us much, right? Tiny little blobs, tiny things. There's no detail to this idea. It's just a starting point, and it's an idea that's probably thousands of years old. The Greeks came up with it, so we credit the Greeks as sort of having the initial idea. That's why the word comes from the Greek language, right? And then over the years, well, actually not much happened for quite a long time, but once we hit into the 18th and 19th centuries, when we've developed, first of all, a better way of thinking about things, something called the scientific method. And also, we've developed, or beginning to develop, new ways of looking at the world where we can see things with instruments and machinery and detectors and things that allow us to see more than just the eye. We see this sort of model going from this into an idea that there is some kind of liquidy goo inside these atoms. These atoms are filled with some kind of juice. I'm going to call it electric juice. They didn't call it that, of course. They didn't really call it much of anything. They just came up with the idea of some kind of fluid. I guess they would have used the word. It's like a fluid, right? That's inside there. So, okay, and then what? Well, then that idea turned into the idea that the electric juice came in two types. There was one kind of electric juice, which was called positive juice, or fluid, and then there was another kind that they called the negative fluid. And so the beginning of those two terms, positive and negative, but at this point, they didn't mean what they mean now, of course. They're just ideas, right? And then, let me just kind of, I'm going to go this way so I can not have to keep moving the board. The electric juice sort of, it was like, well, what is that? You know, they started to envision ideas about what that might be. And of course, they came to the sort of model of the atom that you started learning about in grade 9, where there's an atom, and it essentially is full of this green positive sort of juice, or whatever it was. Let me get a crayon here, and I can sort of shade it all in like this, but I'm leaving some holes. See that? I'm leaving some holes where I shade so I can put things in the holes later. So shade around as if there were holes. So this is sort of the positive matrix of the atom. There we go. Shade, shade, shade. And embedded in it somehow are the little pieces of the negative juice, but they weren't considered to be little pieces anymore. They were the negative particles, right? In fact, they called them corpuscles at first. It's like that. So it's the same idea, but it's changing its sort of, the way it's put together. And then we change the model to reflect the idea that it was not positive juice. Oh, this, by the way, this was called, I should write this, this was called the plum pudding. Plum pudding model. Because we don't eat plum pudding very often, but you can imagine like a pudding or a yogurt with little plums in it or little blueberries in it. Sometimes we call it the raisin bun model because it looks like a bun with raisins in it, or a chocolate chip cookie or something, right? That's kind of the idea where the dough or the bun, the bready part, is the positive and the negatives are like the little chunks inside. Well, then eventually that turned into the positive being actual little particles too. It wasn't like that. It was more like these particle guys, these positive things were also little corpuscles that existed. And we still didn't really know about these negatives. They were in there too somehow. But the idea that they came in little blobs, not in a generalized sort of cookie dough type thing, but everything was little blobby chunks. And then, of course, we get down to the experiments of Rutherford, who was able to sort of understand that the middle part of the atom, which was very small, is where we find the pluses. So remember, on this paper, or on your paper, I'm drawing these colors, and you may not be drawing them as colors. So instead of green dots, maybe you should draw greens with a plus inside, right? And draw these with a minus if you don't have colors, so you know what I'm talking about. Keep track of the different charges. So maybe I'll do that from here on in just to help us, which means I need to change how thick my line is here. Okay. So we have these little, I don't think it changed. Thought it did. There we go. Right? These are the pluses. The positive charges are sort of in the center part of the atom, which we call the nucleus, which is basically just a word that means the center. And then somehow the negatives are on the outside of the atom. Oh, change color, change the line. And the negatives are sort of buzzing about on the outside like a swarm of bees. And it was proposed that they took paths that resembled the orbits of planets. So we get the model of these things zipping around as if they were orbiting, right? Orbiting the nucleus somehow. And this is basically what's called the Rutherford model. And it was Rutherford, and you'll remember Rutherford in his gold foil experiment where he shot the alpha particles at the gold foil and looked at where they bounced. And from what he saw, just like if you were in a dark room throwing tennis balls around, you could tell where things were by where they bounced. He was actually constructing his idea of what this atom might look like by bouncing these tiny little tennis balls or little alpha particles. Well, then, of course, the story doesn't end there. But what's interesting to note is the timeline. We're already up to the early 1900s at this point. And so the rest of the model that's been developed has happened very rapidly. Rather than hundreds and hundreds of years, it's happened in stages that occurred virtually every couple of years. And many, many things were being discovered that helped people build the model further. Now you have to remember that when the Greeks started off, they had an idea, right? This was just an idea. But they had no concrete way of proving it or supporting it or developing the evidence needed to make, in other words, they couldn't show you that this is true. You just had to believe them or not. So that wasn't a very good way of thinking about things. But eventually, when we started getting further into the model, we started to develop the idea that we could do experimentation, right? We could say that like Rutherford could say that this is how an atom looks, and you could just believe him. Or he could show you by doing his gold foil experiment, and you could sit there right beside him. In fact, you can do the gold foil experiment in your basement if you wanted to. And you could watch, and you'd get the same results. And it's the results of his experiment that are important, not so much his idea. The idea is great, but his experiment allows us to have a verifiable sort of evidence that this model or this idea is somewhat valuable. It works. That's the key. We no longer just listen to what scientists or smart people say. What we really do is we see the evidence they reveal. If Albert Einstein himself were to come back from the dead and deny that relativity describes gravity and say to everybody, no, I don't believe that anymore, it wouldn't matter. We would all say he's nuts because his math is already done, right? The experiments have already been done to prove and to support it. So it's no longer about Albert Einstein anymore. It's the experimentation and evidence that show us that this works. And you can deny it all you want, but then you're just delusional. You're a little bit nuts, right? Once the evidence is revealed, it's not about an opinion anymore. And that's very important in today's society where we're inundated with lots of opinions and we seem to think that it matters. Like as an example. Anyway, so back to our Rutherford model here. Then what happens, of course, is new experiments are done. A guy by the name of Max Planck found out that the universe is actually made of little bundles of things. It's not made of continuous, straight, streamy lines. Everything is chunky, essentially. And so then a guy comes along by the name of Niels Bohr. So I'll take this down here like this. And Niels Bohr says, wait a minute. If we apply the chunky idea to electrons around here and everything else and energy, we find that what we really have to do is describe an atom using energy, not a picture of where the electrons go, but a picture of how much energy the electrons have. That's very different, right? And so what he did is he said that there's a nucleus with the pluses inside, but the electrons are now arranged in levels. You can draw a circle all the way around if you want, but typically what we do is we draw sort of a half circle like this. I'll draw it all around though, just so. So this level does not describe so much where the electron is, it describes how much energy the electron has, how hyper it is. It's like a chart instead of a picture. But interestingly enough, the amount of energy an electron has does depend on its position. So it's kind of a weird thing where it sort of tells us where the electron is, this little line I've drawn, but it doesn't really. And I'll get to that in a minute. And then, of course, we learned that electrons have rules. Wolfgang Pauli, who I talked about earlier, determined that electrons work best when they're in pairs. And it has to do with the fact that electrons have a magnetic character. And two magnets go well together, but three just don't, right? It's confusion. For electrons, three is a crowd. And so what we found is that the maximum number of electrons you can have in an energy level is 2e with a minus. And so we drew these pictures in grade 9, right, where we had the first level with the 2 electrons in it. And then, of course, if there's only 2 there, well, then that only works for hydrogen, which has 1 electron, and helium, which has 2 electrons. But when you get to lithium, you have to have a 3rd electron. Where does it go? It can't fit there. And of course, that means it's forced to jump into a higher level. So our model comes down and we have, the nucleus like this. And then we have our energy level. I'll put the 2 electrons in first, right? And sometimes instead of going all the way around, we just draw the level like a half, right? And then you'd have this one up here. So you put an electron up on the top level like that. And this would be the 2nd level. And so in grade 9, you learn that you can build atoms starting from hydrogen all the way up, and you put basically 2 electrons in the first orbit. And then you learn that you could fit as many as 8 in the next one, and 8 in the next one. And then you probably only went as far as calcium, right? And then there was a couple left over for calcium, so you put 2 up here, and you stopped at calcium. You ever notice that? Wonder why you stopped there? if you look at the periodic table at the back of the room, you can see where calcium is. He's sort of at the start of that middle section. He's on the left-hand side, down 4 from hydrogen. Second one in, Ca, calcium. And unfortunately, when you get to there, things get more complicated. So in grade 9, we kind of stop there and say, don't worry about the rest. We'll talk about that later. So that's what you did. And then you drew these little things like this, right? And you called this the Bohr-Rutherford model of the atom. And there were a couple of little rules I'll remind you of. So you had to remember that the number of pluses, or protons, has to match the number of negative electrons, right? And then you also had to know about the neutrons. Another thing I have not mentioned is somewhere back here, just after, in fact, Rutherford developed his model, somewhere between here and where we are now, we also added in the idea of neutrons. Let's put add neutrons here. I don't want to put plus because that sounds... And what the heck is a neutron? Well, the neutron was added because there was some very clever people who discovered that it had to be there. And it's actually fairly complicated what the neutron is for and what it does. But I can give you a general idea, and you should have thought of this. When you were in grade 9, they told you that all these pluses are packed into the nucleus like this. But they also told you that charges that are the same repel each other. And you just accepted that and you wrote it down, but it didn't occur to you that if they repel each other, then how the hell are they staying all together in this nucleus? All of these pluses must be pushing away and the nucleus should just kind of explode. There has to be some kind of magical glue that's working against their repelling if they're going to stay close together. And it turns out that there's a very complex process between the protons and the neutrons. And in order to understand it, we actually have to change our model and imagine that the proton has smaller pieces inside of it, pieces called quarks, which we don't get to until grade 12. But we can understand that the neutrons, their job is basically to interact with the protons in such a way that they overcome or they fight against the repulsion and they pull or keep the nucleus together. So the neutrons are in there as well, and they're like a kind of glue. They're not glue, but they actually react with protons. Well, they interact with protons. And in their interaction, they keep everything held together. But again, you have to wait till grade 12 to fully understand that because it's fairly complicated. So now we just acknowledge that they're there. You'll also notice that the neutrons don't really have the same pattern. The protons and electrons are always the same number, but the neutrons could be a little bit more, a little bit less than the protons, right? They're not always right on. And so we developed a little rule that you'll remember. If you wanted to draw an atom, there are two important numbers we keep track of. One is called the atomic number, and it's just a way of, that says number, not mumber, but on the board it looks like, there we go. It's just a way of putting them in a chart, putting them in order. And so the atomic number is equal to the number of protons that the atom has. So the periodic table starts at 1, and it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, all the way up to 100 and some, based on how many protons you have. Simple. Then we have another number called the atomic mass. The atomic mass is an indicator of the size or the amount of matter that the atom holds. So the atomic mass number is on the periodic table as well. It's the little number, usually it's underneath, or it's different from table to table. You have to look at the key of each table to determine where the numbers are. But the mass number is important because we can figure out the neutrons by using those two numbers. Because if the mass is the total amount and the atomic number is the protons, well, if you subtract that, whatever's left over must be the neutrons, right? And then you're thinking, well, what about the electrons? Well, the electrons are so tiny compared to these guys that they really don't matter much in the mass of the atom at all. So we can kind of ignore them for now. So the atomic mass number can be used, and the rule you learned was if you take the atomic mass number, atomic mass, and you subtract the atomic number, that will equal the number of neutrons, right? And then the last rule, which is kind of related to the first rule, the atomic number is the number of protons, but it's also the number of electrons when the atom is neutral, when the atom is just doing its thing. Okay? What we're going to find out is that atoms are never in this alone state, except for the noble gases. And we're going to see how the arrangement of their electrons determines whether or not they can be stable alone. And only the noble gases, helium, neon, argon, krypton, xenon, and radon, right? Only those ones can be alone. All other atoms never float around alone. They always join up. And we'll talk about the reasons why they join up very shortly once we start talking about their bonding and how they do that. But for today, we just want to review what they sort of modeled, what the model looks like. So let's just review how we would use these rules in this model to give ourselves sort of a picture or a chart of an atom and the energy of its electrons, right? So we would look at an example. Let's do lithium. Okay? And so if you look at lithium, you'd have to look at the periodic table. So I can go to the internet here, and I can probably just Google a periodic table that we can look at. Really quick images. We need something that has both numbers. I think this one will work. Nope, that's not going to work. It's going to give me trouble. I'm just looking for a freebie here that we can use. Usually when they have little squares on them, they're not free. I just wanted to show you how to use the numbers. So. Kind of annoying. Let me pause for a second. All right, well, I found this image here. It's hard to see, so what I'm going to do is just I'll show it to you, and then I will. So right here is lithium, right? It's kind of sideways, and you can't read the numbers. So what I'm going to do is I'm just going to rewrite lithium as it looks on the periodic table, okay? So we'll close this and go back to our thing here. So we have lithium, that's the name of the atom. So when we look on the periodic table, we find a big box, and we find the symbol of lithium, which is Li, okay? And of course, remember, you have to draw these symbols precisely as they are, because they're not, they look like letters, and they kind of are, but they're symbols. And they're international symbols, which means people who don't use the same letters as you also have to understand them. So you can imagine if there was a Chinese character, I'll make one up here, that looks something like this. And you wrote it, and you're like, yeah, well, I didn't put the dot, right? I just did this, which looks similar. That could be a whole different word in a Chinese language, right? So you can't just change it. So to a person who speaks Chinese, this looks weird. They don't use these letters. And if you write lithium as little l with an I, they would see that missing, this part right here, and they would say, that's not the same. Or if you wrote L capital I, they would see it's not the same. And so it's very important, believe it or not, that we don't use our little stylish handwriting techniques. You can't write lithium with a smiley face on top because you like to put smileys on your eyes. You can't do that. It has to look exactly like that, like it is on the periodic table. It's very fussy. And that's because it's an international symbol, and it's for everyone, not just people who use these particular letters, right? So you have to remember to draw those symbols very specifically. Big letter and little letter, done the way it looks on the table. So that's kind of a little note to remember. Okay, and now you would see there are a whole bunch of different numbers. Okay, so when you look at the periodic table, you can figure it out. So if I use the one in our classroom here, we've got all the numbers. There's a key at the bottom, which tells us what all the numbers mean. So when I look at the key, I see that the atomic number is right there, the big red one. And then I look around and I see that the mass number is right here. Now they call it the atomic weight on this table. It's sometimes called that. But atomic mass is a better way to describe that, right? So when you look at lithium, it's 6.941 and a 3, right? So the number that we're looking for is a 3 up here, and then down here underneath there'd be a 6.941. And you have to use the key to figure out, because there'd be lots of other numbers too on your periodic table, melting points and boiling points and all of that. And so they're not always in the same place. You got to look for them. So this one, though, in red is the atomic number. And the blue number is the atomic mass, or sometimes the atomic weight. Weight and mass are not quite the same thing, but they're very closely related, and they are sometimes used interchangeably as long as you are willing to make some assumptions. So that's why that's like that. Okay? And so we can draw a picture by using those two numbers. All right? So what we do is we draw our nucleus, and inside the nucleus is where we find the protons. And the atomic number, the red number 3, is what tells us how many protons to put inside. So we could draw 3 little circles with pluses in them. You can use a P. There's lots of ways to describe them. But drawing circles is good if it's small. But when you get up to like lead and you got to draw, a whole bunch of circles, it's too confusing. So usually what we do is we just write a number. And we put 3, P. And sometimes what I'll do is when I'm teaching grade 9 and 10 like this, I put a plus beside the P to remind us that those are the positives. 3P plus. Okay, that's easy. You just look at the number. Now, to get the number of electrons, we'll do them after. We'll do the electrons last. To get the number of neutrons, which are also inside the nucleus, we take the bottom number, the blue number, round it off, and then subtract the red number. So we take the 6.941 right here, and we say that rounds off to about 7, and so we write 7, take away that red number 3, and of course that equals 4. So we put 4 neutrons. So I'll use a different color here, and we'll put 4. And the neutrons, you just put a little small n, because they don't have a plus or a minus. That's the interesting thing about them. Neutrons are neutral. They do not have any kind of electrical juice. Right? They're neither one. They're missing. That's not part of their personality, so to speak. Okay, and then we have to now put the electrons on. And they're a little bit trickier because they follow that pattern. The pattern I showed you before of Rutherford's or of Niels Bohr, right? And when he put them in. And so we have to remember that there are levels here. The levels are sometimes called orbitals because originally they were like orbits. And when we changed our understanding of them, we changed the word slightly, but it still sounds like orbit, so it's kind of a bit confusing. But an orbital is actually a word that just simply describes the energy level. But it can also describe, as we'll see shortly, it can also describe sort of like the chances of where you could best find the electron. We'll get to that. So we draw here a level 1, right? Level 1. And it could go all the way around, but I just left it like that, because otherwise your picture gets too big. Now, how many electrons are there in total? Well, this is it. The number 3, the atomic number, tells us there's 3 electrons. The electrons always match the number of protons, because we're drawing the neutral atom. It's an atom that is theoretically by itself. So I have to put 3 in here. But the problem is we learned that only 2 electrons can go in each level. So that means that I can only put 2 in the first level. So I can fill it up. We say once there's 2 electrons, it's full. I put a minus to show that electrons are minus. So where does the other one go? Well, the other one must go up. It must bump up. Just like if you go to a hotel and the first floor rooms are full, even if you're afraid of heights, you got to go to the second floor. So you bump up. So the next electron would bump up to the next level. And we would put them in here, in the second level, and we would write 1. And then we stop because we've hit 3. See, we've hit the 3. If we had a bigger atom, whose atomic number was 12, well, then we'd put 2. That would leave us 10 more. And then what would we do? Well, we can't put 10 in here. The second level, the maximum, if you think about the levels, they are 2, and then the maximum is 8. And then 8, this is what you learned in grade 9, right? And I'm going to explain to you why it's 8, because it should be 2, right? How can you fit more than 2? Well, because the second level has 4 little sub-levels hidden inside it, and each one has 2, just like the rule. But the total is 8. And we're going to see how that works shortly, when we maybe tomorrow. When we study a little bit about the quantum mechanical model, which is an improvement on the Bohr-Rutherford model. But for grade 9, you can use this little reminder, 2, 8, 8. And then the system sort of breaks down because you can't go much past calcium without getting into some issues here. So we'll just kind of leave it like that. Any questions on how to do this from grade 9? You guys remember this? Okay, so here's what I'm going to leave you with, this task, right? I'm going to ask you to draw a Bohr-Rutherford picture for any 10 atoms you want to pick between atomic number 1 and 20. So you don't have to do 20, but you do 10. Pick 10 between hydrogen and calcium, right? The top ones that go across your periodic table. Do all of you have a periodic table? Maybe, maybe not. I got one in grade 9. What I'll do is tomorrow I'll get you one, but for tonight, you can just look one up online and use the key to find the atomic mass and the atomic number to figure it out. And then try and just to practice reminding yourself, arbitrarily choose any 10 atoms somewhere between here. And that's it for today.